In this project, I will demonstrate how to wake up from low power mode using 32-bit interval timer. Open Escape Studio, then click on this file icon, then select New, then select NSS C++, then select NSS RA project. A new dialog box will appear. You can give name to your project. After naming your project, click on this next button. Here select FPV RA0E1 board from this drop down menu, then click on next button. Here select none option, then click on next button. Here select executable and no autos option, then click on next button. Here select bare metal minimal, then click on finish button. Now IDE will take some time to configure your project. After project configuration, by default IDE will open FSP configuration file. Now open stack tab, then click on new stack, then click on power, then click on low power mode stack. Now click on low power mode stack, then open its properties. Now expand general tab, and for low power mode select software standby mode. Now scroll down and expand deep sleep and standby options. For wake up source we can select 32-bit interval timer interrupt option. Now again click on new stack, then click on timers, then select 32-bit interval timer stack. We are getting error related to clock source for timer stack. Now open clocks tab, then scroll down to find options related to timer source clock. For FITL0 source we can select loco option. For FITL1 source we can select high speed on chip oscillator. Now you can observe in stack tab that error related to timer stack is resolved. Now click on timer stack, then open its properties. In properties window, enable support for 16-bit capture mode and interrupt port. Now expand general tab and select 32-bit counter mode. Now expand interrupt tab and select priority for your timer interrupt. Now click on BSP tab and scroll down to find subclock drive option. For subclock drive option, we can select low power mode too. This will reduce further power consumption in low power mode. Now we don't need to change anything further in FSP configuration file. Click on generate project content, then click on proceed button. Now expand src folder and open hallentry.c file. In Project Explorer window, expand Developer Assistant tab, then expand Low Power Mode stack. From Low Power Mode stack, drag and drop Low Power Mode open function call in hallentry.c file. Now declare FSP error variable to check status related to function call. Now use assert function to make sure low power mode open function call was successful. Now in Project Explorer window, expand gtimer stack. Now from Developer Assistant tab, drag and drop timer open function call in hallentry.c file. Now use assert function to make sure timer open function call was successful. Now I am defining a variable that will store time in seconds for which MCU will remain in low power mode. I am initializing this variable to 15, so MCU will remain in low power mode for 15 seconds. Now I am defining these three variables here: reset value, periods count to update timer period when the interrupt will be generated, and the info variable to get timer information. Now from Developer Assistant tab, drag and drop timer info get function call in hallentry.c file. For second argument, we need to provide the address of info variable. Then use assert function to make sure timer information get function call was successful. For period count, we can multiply clock frequency with time to wake variable. For every clock cycle, timer counter will increment. To count up to clock frequency, it will need 1 second. So when we multiply it by 15, this will set the timer period to 15 seconds. Before updating the timer period, we need to call timer stop function call. From Developer Assistant tab, drag and drop timer stop function call in hallentry.c file. Then use assert function to make sure timer stop function call was successful. Now from Developer Assistant tab, drag and drop timer period set function call in hallentry.c file. Now use assert function to make sure timer period set function call was successful. For normal operation, first I will blink onboard user LEDs for some time. After that I will start timer counter and then I will enter in low power mode. Now I will declare while one loop here. In while one loop using for loop I will call a function that will blink onboard user LEDs. Now I am defining a function named LED blinking. Also, we need to define the function prototype. Now in Project Explorer tab, expand GPIO stack, then drag and drop GPIO pin right function in LED blinking function. For second argument, we can use LED1, and for third argument, we can use BSP IO level high variable. We can copy this function call and change the second argument to LED2 for second onboard user LED. Now define FSP error variable and use assert function to make sure pin right function call was successful. Now using RBSP software delay, I will introduce a 200 millisecond delay. For first argument, I can use 200, and for second argument, I can use BSP delay unit millisecond. After 200 millisecond delay, we can turn off the user LED by using above pin right function call, then changing the BSP IO level to low. After turning off the LEDs, we need to again provide 200 millisecond delay. Now in for loop, we can call LED blinking function. Now from developer assistant tab, drag and drop timer start function call in entry.c file. Then use assert function to make sure timer start function call was successful. Now from developer assistant tab, drag and drop low power mode enter function call in entry.c file. After that, use assert function to make sure low power mode enter function call was successful. Now the programming part is complete. Click on your project name, then click on this hammer icon to build your project. I am reducing the for loop iteration from 20 to 10. After project build is complete, right click on your project name, then select debug as, then select NSS GDB hardware debugging. Now click on switch button to open debug perspective. In debug perspective, click on this resume button twice. I have attached an ampere meter to CN30 to measure current consumption in low power mode. In video, you can observe that when LEDs are blinking, RA0E1 controller is consuming almost 4 milliampere current, and when RA0E1 board goes into low power mode, it is consuming around 30 microampere current. The change in current consumption and LED blinking after every 15 seconds verify that our program is working successfully. Timer interrupt is waking RA0E1 board from low power mode to normal mode after every 15 seconds.